We talked a little bit about inverse relations yesterday and then brought up this idea of inverse functions. So let's look at inverse functions in a bit more detail because we're probably more interested in those at the end of the day, the ones that do turn out to be functions. Now the symbol we use for inverse functions is actually a -1, so don't confuse it to be the power of -1. That's why in trig we have the reciprocal ratios, because you know how in trig you write the power above the trig, so like you go sine squared x rather than sine x all squared. So if it was to the power of -1, you can't go sine to the power of -1 because that means inverse function, and that's why we have the reciprocal ratios, so we don't have that confusion. So the symbol is a, what do they call them? Superscript. Is a superscript of -1. The composite function of a function and its inverse function should always turn out to be x. So if you substitute the inverse function into the function, x. If you substitute the function into the inverse function, x. Because inverses should cancel each other out. So let's try one. Let's say the function is x minus 2 on x plus 2. It's our basic hyperbola, but it's been shifted. Because if you were to do a polynomial division on that, we'd end up with 1 minus 4 over x plus 2. So it's our basic hyperbola, shifted across a bit, shifted up a bit, and flipped. But I guess what I'm getting at, because I know it's a basic hyperbola, it will satisfy both the horizontal and vertical line test. All right, so let's find it. X equals y minus 2 on y plus 2. We want to make y the subject. Multiply by the denominator. Expand out. Group everything that has a y in it together and then divide by that factor, and we come up with, well, as we would expect, another hyperbola. Because if you're going to reflect a hyperbola, you would get a hyperbola. First of all, let's substitute in the original function into this inverse function and see what we get. Ugh, fractions on fractions, yuck. Multiply everything by the denominator. Let's get rid of those denominators on the denominators. So multiply everything by x plus 2 and a little bit of algebra, but sure enough, we end up with x. Let's go the other way. So now we'll substitute in our inverse function into the original function. Again, let's get rid of the denominator. Multiply everything by 1 minus x. Bit of algebra, tidy up. Yep, we get x. So that's what we should see happen every time. Domain and range. Remember we said we're swapping the x and y's. So if AB is on the function, then BA must be a point on the inverse function because the x and y values swap around. Therefore, and we mentioned this yesterday, the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. So let's have a look at a couple of examples. Here's our basic exponential, y equals e to the power of x. We know its domain's all real x. We know the range is y is greater than 0. Swap the x and the y's. We've got x equals e to the y. Make y the subject. The opposite of the exponential is the log function. So we get y equals log x. The domain of that then should be the range of the original, so it'll be x is greater than 0, and the range should be the domain of the original one, so it should be all real y. If we were to reflect it, there we go. And we have a beautiful reflection in the line y equals x. And in fact, there's no points of intersection on these ones. That was nice because it satisfied the horizontal and the vertical. But if you think about it, most functions will not satisfy the horizontal because most functions turn somewhere, come back down. And as soon as they turn and come back down, it's going to fail the horizontal. So it'll only ever satisfy it if it's what we call continually increasing, so it's always going up, or continually decreasing, it's always going down. That's the only time. So we need to, in order to create inverse functions, we need to restrict the domain so that our function, we just look at a piece of it, and that piece will be one-to-one. It will satisfy both tests. So all right, how do we pick it? We have a look at your graph, and you pick a piece of it. But in that piece of it, You want to get as much of the range, hopefully you get all the range, but as much of the range as possible. But it's that idea again, you've got to pick a piece that's continually increasing or continually decreasing. So it will satisfy the one-to-one. So let's start with the parabola. There's y equals x squared. We know the domain is all real x. We know the range is y is greater than or equal to 0. Terrific. But it's going to fail the horizontal line test. No good. So it doesn't have an inverse as it stands. I've got to pick a piece of the parabola which is either continually decreasing or continually increasing. Where shall I pick? What x values will I go for? Greater than or equal to 0. That would be a possibility. What would be another choice I could make? Yeah, less than or equal to 0. So less than or equal to 0 would be continually decreasing. Greater than or equal to 0 would be continually increasing. In this situation, because both of them are going to get me the complete range, we tend to go with the positive rather than the negative. So I'm going to restrict it to x is greater than or equal to 0. Now the range will still be y is greater than or equal to 0. It's not going to change. I still get the same y values. So all right, let's work out what this inverse function is. Swap the x and the y's around. It's y equals x to the power of a half. It's no longer plus or minus the square root of x because we've restricted the domain. First of all, let's work out our new domain and range. Domain and range will swap around, although, okay, probably a bad example of that. Trust me, they have swapped around. The original domain is x is greater than or equal to 0, so the new range is y is greater than 0. The original range was y is greater than or equal to 0, so the new domain is x is greater than or equal to 0. Trust me, they did swap. All right, there's y equals x. If I reflect it, I get that parabola on its side, so x to the power of a half. There is another way you could go and find the range of a function now. And we just said the domain of a function is the same as the range of the inverse. But we also said the range of the original function is the domain of the inverse. And people tend to find domain easier to find than range. So if you have to find the range and you're going, hang on, that's a bit tricky, maybe it's easier to find the domain of the inverse, because then you know that will be the range of the original function. So something like, well, okay, let's pretend we don't know. Ooh, y equals x squared. Oh, what's that going to be? Okay, I change them to capital X and Y so I don't get confused which one I'm working with. So swap them, we get capital X equals capital Y squared. Now y is equal to the square root of x. The domain of this new function is capital X is greater than or equal to 0. So that's the domain of the new function. So it should be the range of the original function. So therefore the range of that original function, if I couldn't find it, there it is, y is greater than or equal to 0. X squared plus 3. Again, swap the x and y's around, but I'll make them capital so I don't get confused. We got y equals the square root of x minus 3. So the domain of the new function is x is greater than or equal to 3. Therefore, the range of the original function must have been y is greater than or equal to 3. Y equals the absolute value of x plus 2 minus 5. Okay, swap the x and the y's around. Got to make y the subject. So x plus 5 is equal to the absolute value of y plus 2. So x plus 5 must be a positive number. So x plus 5 is greater than or equal to 0. So the domain of the new function is x is greater than or equal to negative 5. The range of the original function, y is greater than or equal to negative 5. Square root of 4 minus x squared. X is equal to the square root of 4 minus y squared. Play around with that one, we eventually get y is equal to the square root of 4 minus x squared. Domain of my new function, x is in between minus 2 and 2. But, and this is where we've got to be careful on this one, but the y values, the original y values, we know they're going to be positive because I'm saying the positive square root. So I can't just say then that the range of the old function was just in between minus 2 and 2 because we know we can't get negative numbers. So I've got to take that into account. So it's not a foolproof method. Sometimes you do have to be careful and consider some other things. But it does give us another way. Let's try one of those hyperbola ones. X plus 7 on x plus 4. Swap the x and the y's. Eventually I get y is 7 minus 4x on x minus 1. The domain of that, all real x except x, equals 1. Therefore, the range of the original one must have been all real y except y is equal to 1. That one's fine. 5g